Welcome. This is the crime investigation, the Trojan Caper homework number 1, and this is the solution walkthrough. A roll-up of what you should know about Trojan horse circuits. There are 2 points of view on Trojans. The Sherlock Holmes method. This is an individual who likes to think their way through the scene of a crime using deductive reasoning, or the Inspector Clouseau method. He's kind of like a firefighter who puts out the fires and the flames. He stumbles over the crime and tries to figure out from visible evidence. So the guide to the homework, it is all about what is being investigated here is your understanding of the concepts and your thought processes. So completing the homework will contribute to the grade. In most cases, there are no wrong answers if you put on the black hat and think like a nefarious and malicious individual and justify your answers. Think motive, method, and opportunity to become your inner criminal. So here's an example homework problem that can be used to understand the concerns about Trojans and triggers. The topic of concern is the built-in security vulnerability, the Trojan or Trojan horse. A circuit, device, and product example without a Trojan, a circuit, device, product example with a Trojan, a choice of triggers used to activate the Trojan, and then a set of questions concerning Trojans and triggers and the reasons for taking the risk of placing them in an IC or product, and that's an integrated circuit. So before the introduction of the homework problem and expanding the solutions, here's the threat universe for hardware. The threat universe covers all of the potential security vulnerabilities or breaches associated with hardware, the ICs, the boards, the systems, or the products. Note that there are separated into categories, so this does not mean that they are implemented individually. In many cases, there may be more than one member of the threat universe applied at the same time. Note also that the existence of a threat when applied or implemented is generally known as an attack or a security threat. So when solving this particular problem, don't just think in terms of Trojans. Okay, they're trying to make this as realistic as possible. And again, this is the graphic here depicts hardware, the genetic versus the external injections, and these are all of the different types of things going on here. Hardware security threats are many in nature, and they may not always be delivered individually. Sometimes there's a mixing of threats. A backdoor can be used for tampering. A counterfeit device can be a Trojan. A Trojan or backdoor may be an opportunity or vulnerability that would allow a virus to be implanted. So here's a portion of the hardware design. This portion is an example of a board level design. And this can be seen as a scale involving having 3 inches inside of an integrated circuit. So they're kind of zooming in on this image. This design shows 2 microprocessors that have high-speed bus, usually a PCIe bus, but could be a USB port, a gigabit Ethernet port, or even a SATA port. And because of the physical distance between the devices, they use a retimer chip. A retimer chip must be used because the high-speed signal, which is a low-voltage differential signal, we call it a LVDS, degrades over distance, and must be refreshed or retimed. The higher the speed or bit rate, the shorter the distance before needing refreshing. So, for example, a 2.5 gigabit signal can travel further than a 25 gigabit signal. Note also that the board subassembly here is shown with a JTAG port and an I2C port. These are both test and settings configuration ports that are used to put the chips into various test configurations, or can also be used to select operation modes. So one strategy for opportunistic hardware security attacks on the board or system is not target the big complex chips in the system, as they already go through extensive scrutiny and during the design and test, but it's about attacking the small, ubiquitous support chips in the system. These types of chips can include functions such as voltage regulation, clock extenders, signal spreaders, and other chips that allow the large, expensive major chips to operate in stable environment and enables them to communicate with each other. One such chip is a high-speed serializer-deserializer based LVDS retimer. Since the retimer is used in the data pathway to refresh the data signal's voltage, timing, and equalization, all of the data from one major device to another passes through its data refresh circuitry. That is the PHY, physical interface, and turns them into parallel data in a MAC, media access controller, in a serial to parallel operation. It also checks for correctness using the ECC error correction codes. Then passes them back out through a MAC or PHY on the TX, and that's the transmit side in the parallel to serial operation. So the retimer is the gatekeeper. The main usage of a retimer chip is to conduct clock recovery. When data is transmitted from one chip to another, there are three ways to conduct the transfer. One method is to send a clock signal from the source chip. So a microprocessor would send a data signal based on its internal clock and will also export the clock signal, and the receiving device would use both the data signal and the clock signal to capture synchronize the transmitted data. And this method is known as the source synchronous data transmission. A second method is to have a clock signal generated at the board or system level and to feed this clock to all devices. All chips synchronize data transfers to the same clock. And this is known as system or clock synchronized data transmission. These methods both have problems with distance versus clock skew. A clock edge may be viewed to occur at time 0 at the source of the clock signal, but as the clock propagates across a distance, the clock signal gains delay and the clock edge moves relative to the time 0 edge. At a far enough distance, the edge may move a whole clock period, and so data at that location would be one clock cycle delayed from data at the time 0 point. And let me get back in there. So At a far enough distance, the edge may move a whole clock period, and so the data at that location will be one clock cycle delayed. If the data must be processed and returned to the chip that originally sent it, then the return data could be 2 cycles delayed. And for a system that is managed by clocks and expects data to be fully synchronized, this could be a huge problem. The third method solves this problem in that each chip has an internal clock generated internally through a PLL or DLL, delayed lock loop. The clock recovery signal is embedded within the data so that the transfer is fully asynchronous. The data is created with the source clock, and the receiving device extracts the data with its own source clock. Now, the next slide actually shows a company that actually builds retimers and chips, and this is from the IDT, the Integrated Device Technology, and these guys manufacture, ship, and put them into the boards and things of that sort. There are reputable companies that make and sell retimer chips. They provide a data sheet to show the features and operations and settings associated with the retimer chips. Being a reputable and valid company, and since these retimer chips are a part of their portfolio of parts, they would not knowingly provide security compromised chips, since this would compromise their reputation, and since the customer for these chips is also the customer for their many other chips. So one of the strategies companies that make counterfeit chips is to target a reputable company by making fake chips and going through meticulous detail to achieve the same dimensions, package types, ceramics, logos, and other stamping details. These chips can then use the good reputation of legitimate companies to sell their fake products. Fake products or counterfeits can have several levels of fakeness. They can be real products reclaimed from discarded electronics and cleaned up, so they are real parts but have some lifetime used up. They can be real parts but repurposed for other bins, such as 3-core or slow part being repackaged and sold as for 4-core or fast part. They can be real parts but reclaimed from discarded or failed parts from the manufacturing process. So for example, they may be parts that were rejected for stuck at faults, excessive current leakage, or delayed timing faults. They could be completely fake parts made in road fab by either a mass cloning legitimate part manufacturer or by designing a part that implements the publicly available data sheet. So here's part one. The compromised device in this design is a retimer with a Trojan on the PCIe high-speed lane. Since the retimer needs to receive data from multiple sources and transmit that data to multiple sinks, endpoints, it sees all data traffic passing between these chips. The black hat designer, in this case, has taken advantage of this access to all data and has placed some significant security breaches resources between the two MACs. The RX MAC on one side of the receiver that receives the signal, and the TX MAC on the other side that retransmit the retimer signal. The Trojan circuitry includes the ability to compare the data to known data patterns, so what we call snooping, and also store the data for viewing or use later. The ability to generate fake packets or to substitute an existing packet with a fake packet. And then 3, the ability to manipulate the data rate by allowing the retimer to assert its bit error rate signal to indicate corrupted data, even if the data is pristine and not corrupt. and this puts the attached TX in the mode to retransmit the identified packet continually until the BER signal is deasserted. So part 2, although not specifically mentioned though, this design, it is assumed that the Black Hat designer included the ability to do these things through either commands that come through the I2 port or through specially manipulated data packets with command headers coming through high-speed data channels. Note that this amount of Trojan hardware is significant and represents a major investment by the producer. So this Trojan logic was not inserted from within a legitimate retimer design house. It couldn't have come from the IDT or the TI, Texas Instrument, because it would have been discovered during the evaluation of the mask before production. There could not be this large amount of added logic without it being found out. So this leaves the case where a rogue fab foundry must have designed and made the part and placed the TI or IDT logo on the package. In short, the device is a counterfeit that is full of Trojan capabilities. Even though this diagram shows the usual place for counterfeits to be introduced, is it at the packaging or the assembly house? As most counterfeits are repackaging for existing parts that have either been reclaimed from discarded electronics or reclaimed from manufacturing reject bins. But for this particular case, there is a rogue fab foundry that has designed and manufactured a fake part that includes significant Trojan logic. When this part arrived at the legitimate packaging assembly house, the packager didn't know that the part wasn't from IDT. They may have thought it was legitimate. All right, and then also the distributor received the box of parts from the packager and warehoused them in anticipation of fulfilling orders with legitimate parts. Other facts that go with this line of thinking: the rogue fab foundry must have a related design house. The size of a retimer is fairly small, so in a normal wafer run, they're made up of sub 90 nanometer nodes, could result in 2,000 or more die per wafer. If the process was stable and achieved an 80% yield, then just one wafer lot will produce 40,000 good parts. That's a lot of Trojans to distribute into an electronic product. This number of die being sent to a packaging house would seem to confirm to the packager that this order represents a legitimate product. So the answer to number 1, it says number 1, from the board level point of view, where in the embedded circuit supply chain did this compromised retimer come from? And then also why? The complex Trojan infested retimers came from a rogue fab foundry with their own ASIC design group because the part has too much Trojan content to have come from a legitimate design organization that supplied retimers. All right, now this is the scene of the Trojans in the silicon process. So this is more from the IC point of view, where there are different opportunities to insert Trojans, and there are certain opportunities where Trojan detections are very opportunistic. And since the entire design was copied from a legitimate company and with significant Trojan content inserted, the Fab Foundry ASIC design group designed this chip. The counterfeit part was not made by cloning a mask, so not in here. One thing that could have happened is that the Fab group assisted a legitimate design house in making a chip. With this type of agreement, the Fab Center personnel would have access to all the design files under the guise of getting the design ready to go into a specific fab, with certain design rules and restrictions. After a legitimate part is made for a customer, the design files can be used to make counterfeit parts, or the design files can be used as the basis to make similar or Trojan-infested parts. Therefore, this whole integrated circuit design to implementation flow was compromised. The Trojan was most likely treated as part of the functional design. So, for this particular part, there are arguments that could be applied that the source of the Trojan and its trigger be from any portion of this design flow. The easiest, given that this is a fab, is that there is an RTL, a register transfer level model block of the Trojan logic that must go through synthesis and place and route, or that there is a physical macro of the Trojan and trigger circuitry that already exists and is placed, attached, and connected during physical design. So the answer to number 2 would be this retimer was designed as a functional chip using this whole flow, or this retimer was a pre-designed macro that was connected to a stolen legitimate design during physical design. So here we have the Trojan payload taxonomy. When this device is placed on a board, it is thought to be a legitimate part. If the part proves to be problematic in design, implementation, or use and is investigated, it may be found that the Trojan is a Trojan-infested counterfeit. From the board point of view, the chip will be labeled as a counterfeit, not so much as a Trojan. So the question to number 3 is, from the board point of view, what is the category of the Trojan? And the answer is basically the chip from the board design point of view is a counterfeit. The source company, we can call it IDT, will investigate the counterfeit and will determine that it contains multiple security breaches and can conduct all 3 main functions: leak data, structure information, and modify code, and impact reliability. The effort to mask or hide the Trojans during design and tasks may not have been done, but it is highly unlikely that the normal board design engineer will suspect all of the Trojan content, so no real effort or extra subterfuge has been attempted. Question 4. Now, from the integrated circuit point of view, what is the category of the Trojan inside the retimer? And what we could say is that the Trojan contains content that can leak data information, modify behavior, and emulate a reliability impact because the part is a whole counterfeit device made to emulate a legitimate device. There has been no real effort to specifically hide the Trojan content inside. All right, so now we're getting into the Trojan and Triggers match game part 1, and there's also 2 questions. that we're going to get into as well. So, as mentioned earlier, this Trojan is a complex unit attached to the data pathway. It is most likely that the data is being investigated between the RX MAC and the TX MAC, where the data is processed in its parallel and slower form and is not in packet form. The Trojan capabilities or payloads means that the data can be captured and compared, the data can be stored, the data can be modified, the data can be replaced, and the data can be reported as corrupted, whether it really is or not, or any combination of actions. The setting up of the action or Trojan payload to be accomplished can be done either by establishing the settings and compare data values through the I2C port, or if the Black Hat designer put an effort into thinking through the usage scenario by special command packets through the normal data path. So, what is the most likely triggering mechanism for this type of Trojan? Since the data path is the focus of the attack, then the trigger involving the data path is the more appropriate trigger. Since matching one data value may occur many times, it may not be advisable to set a trigger for a single data match. But observing sequences of data to identify when certain types of data is present on the data path, or maybe when a specific sequence occurs, to tell the Trojan to implement its program payload. Another item to consider is the scenario where or when does the Black Hat hacker want to set off the trigger. As was mentioned earlier, there'll be a minimum of 40,000 Trojan injected parts that will either go through a normal and non-corrupted distribution chain, or will go through a specific corrupt distribution chain to get the parts into the certain products. If the parts go through the normal distribution chain, then the hacker cannot reasonably know where all of them end up and cannot manage all of them. In this case, the hacker gets paid a little for the parts, but mostly gets paid by letting others in the Black Hat community know where some of the parts ended up and how to operate them. For parts that the hacker placed specifically, the hacker may only be interested in high-value payback, return on the Trojan investment, all right? The hacker may want to specifically target banking, medical, government, military product development organizations, servers, computer platforms, and all this. The hacker must then decide what the staging, activation, usage, and extraction strategies are. So, first, let's consider exploring the scenario development process from the Black Hat perspective. Number one, there's something called staging. How does the Black Hacker program the Trojan to do the preferred activation for the end environment it ends up within? For example, a bank is programmed differently than a military ship or weapon system, and the IRS is programmed for completely different goals. Number two, activation. How does the Black Hat hacker expect the Trojan to activate? Under what conditions? For example, activation targets may be a bank when credit card numbers are evident, military when weapon codes are being processed, the IRS when SSNs are processed, usage. Number three is usage. For each of these environments, is it collect data, behavior modification, or reliability impact? For example, a bank collect data credit cards and offshore account data. If it's military, we can stop the fire code from being delivered by emulating a broken chip or communication channel. And if it's the IRS, You can modify behavior by changing the data that represents or refund values associated with the Social Security number. Now 4 is the extraction. How does the black hat hacker expect to see the result of the activation? For example, for collecting data, we send the collected information to a memory for direct retrieval later, route collected information to a physical port for immediate collection, route collected information to a radio for remote collection, or send the collected information to a portion of the board that will process it as data and send it over onto the internet to a specific address programmed in the retimer, or etc. So given this complicated thought process, and which happens to be everything a black hat hacker had to think about when designing a Trojan, here's the most likely answers for number 5, from the IC point of view. Which are the most likely trigger or triggers for this Trojan, and why? And here we have any of these triggers could be used. It actually depends on the goal set by the black hat hacker and where, how, and why the Trojan is going to be used. So from this specific list of triggers, the least likely is the life timer. To meet most of the goals of having this counterfeit device with the Trojan infrastructure and various end products, predicting a time frame and programming it at the time of the Trojan's design is very unlikely. It is also very unlikely to need to use a temperature trigger unless it is known that a military device will be deployed to the Arctic or Antarctica, or a satellite will be deployed in space. There are good arguments that it could be a data sequence trigger. It could also be a data match trigger, an RF input trigger, and a hidden input trigger. These triggers allow either remote operation, conditional operation, or direct tampering operation, which may be valid scenarios. The most stealthy and the best use case is the data sequence trigger. And the best staging or programming method is to have built in a set of special commands to allow the trigger to be programmed by delivering special commands to the Trojan through the data channel. The best trigger depends on the attack and the attack scenario though, and that all depends on the black hat. Number 6, does each appropriate trigger match the Trojan function and stealth rating? The data match and the data sequence match both equal the stealth of the Trojan's payload. They use the same circuitry as the Trojan to apply the activation trigger as well. All right, so I'm not going to go through the rest of this because it's just a lot, but I will just run through the slides, the rest of the slides, just so we can kind of get a feel for what's left. So this will probably be the end of this part 1, and maybe what I can do is come back and